Just a second. Okay, that's great. Okay, this is the right place. We're talking about epidermal sensors for the monitoring of the signals coming from the skin to have a more deep insight about the physiological phenomena and also to enhance and even restore lost senses. Along years, sorry, cannot, okay. Okay, a companion of epidermal sensors is the radiofrequency identification, because this technology provides the capability of communication without power. All the energy is provided from remote. And also the electronic complexity is reduced to the lowest one. Along years, we have developed several kind of sensors to collect temperature, sweat, pH, and much more. Should this technology be successful over the large scale, we have to face some important issue, let's say billions and billions of those devices. And so we have to consider the problem of the availability of materials. Making metals is expensive. And then we have to recover this material. We have to dismantle, to reuse. And this will be a problem in the future. So a possibility is to avoid use of metal, say making plasters metal-free. How can we do? We can transform the substrate of the plaster into metal by using the technology of laser-induced graphene. This technology was introduced more or less 10 years ago, and we can start from a precursor material, generally material like the polyimide PEEK, and then by laser we can engrave it, provide energy that breaks the bonds of carbon move toward the surface, and so you can see here the typical leak flakes this way. The conductivity is not so good as graphene, but you can use to make antennas. In particular, the parameters that impact the quality of the graphene is the speed of the laser, of course the power, and especially the focusing which impact on the size of the spot, and so the superposition among adjacent spots. When we move to sensors, which have been already experimented by LEAG to antennas, we have to face a different scale. Particular antennas is much larger than sensors. And while for sensor, you are interested in the change in the sheet resistance, for antennas, performance are related to the nominal value of sheet resistance, so you should be really careful. Moreover, antenna works at higher frequency, and so you could have problems of efficiency. Now, not always when you work with antenna, the larger is better. So you can think to improve the performance by enlarging the antenna. But if you enlarge the antenna, you can essentially improve the directivity, but also the losses. So you can expect a trade-off. So we can expect an optimal size of the antenna. So in this work, I will identify the upper bound performance of on-skin antennas made by laser-induced graphene, and we will provide the first experimental demonstration of a working device. Let's start from this reference antenna. The loop was demonstrated to be the most effective shape for the antenna over the skin, as a balance between efficiency and size. We parameterize the performance in terms of the radius and in terms of the width of this ring. And we analyze the performance over a layered model of the human body with parameters close to 1 gigahertz. So we are talking about UHF, radio frequency identification. And also we consider copper realization for comparison. Here we have an important issue. When working with the laser-induced graphene, the material is not a good conductor. So the penetration depth is larger than the thickness of the material. So it means that this layer is partly transparent to the electric field. So you cannot model as a conductor. So we made a lot of analysis, and the best way is to use the Leontovic condition. Let's say we model as a layer of surface impedance whose resistance can be derived by measurement, and we can neglect the imaginary part. It could provide anyway good results. Now, this is parametric analysis in terms of the radiation gain, which is the performance for an antenna, in terms of radius and width. And we have lead and copper. It is very interesting to notice that, okay, we will lose something about moving from copper to lead, about 4 dB, due to the losses of the lead. But the optimal sides, you know, are essentially the same. So same shape for the lead antenna and for the copper. But for the lead antenna, the width has a larger impact than in case of the copper. Then there is a problem of impedance matching that for antenna designer is a really key point. We have to match the impedance of the antenna to that of the microchip. The microchip has a complex impedance with a capacitive imaginary part, so we need an inductive antenna. And to do this, we add here a loop adapter made by aluminum. Aluminum because it could be useful to avoid additional losses. And we parameterize the matching by, against 2 parameters, the spacing between the loop and the ring, and also the thickness of a substrate layer, a silicon for application over the skin. The parameters is the power transfer coefficient, which should be close to 1. And we have a large region. So overall, this arrangement is not so much sensitive to the spacing. So it's good for fabrication. Manufacturing starts from the polyimide precursor, lysing. Then we remove the unwanted part of the polyimide. We transfer over biosilicon. We assemble with the loop adapter. And finally, we use a polyurethane membrane to cover the device. This is the prototype. You can recognize the typical patterning, rastering of the leak manufacturing by laser. And with magnification, you can see the graphene formation here. It's really soft, flexible, partly stretchable, partly not completely stretchable. Then the evaluation over the skin. By making a comparison with 6 volunteers with different body mass index, so we can have some variability of the body, in comparison with a liquid phantom and a simulation. The comparison is quite well, with a variation of no more than a couple of dB. Then another interesting analysis concerns the sensitivity to the position over the body. Depending on the position, we would have more fat, more muscle, and so on. And so we have positioned abdomen with a small curvature radius on the arm, a medium radius, and on the wrist, a very large radius. In the first 2 cases, the performance are completely stable. While instead, where the curvature radius increase, we could have a detuning. It's not dependent on the material. It's typical of the antenna when you curve, the shape factor produce a change of the impedance. Finally, an experiment. I'm concluding. An experiment with the measurement of the temperature over the abdomen. Here you see the polyurethane to attach the sensor over the skin. And also we included the thermocouple here in the same position, the microchip, to get the temperature, to make a comparison. To modify the temperature of the skin, we used an ice bag placed on the abdomen for 3 minutes. And you see a reduction of the temperature. Then we release the ice bag, and the temperature recovered the normal value. The thermocouple and the temperature collected by the IC is quite correlated. The average difference is less than 0.5 degrees. So it could be useful to collect information on the body. So let's conclude. We have evaluated the optimal size of leak-based epidermal antennas on skin, and the size is close to 3 centimeters. And the size is similar to that of copper. With respect to copper, we lose something up to 4 dB, and in the best case, we are able to reach minus 50 dB. But we also noted that when we introduce the loop match, we lose further dBs. So we have to work carefully to improve the impedance matching in order to avoid power loss. It's very critical when we have antennas over the human body. We have to improve the interconnection with the leak and surface mounting components. Not easy to direct solder or attach the sensor, the device over the leak traces. And we expect improvement when moving from polyimide to polyether ketone peak. We have already made experimentation, so we are able to reduce to 1/4 the sheet resistance. This device could be useful for application over woods, to analyze infections, but also to evaluate the temperature. Okay, that's all. Thank you for the attention.